Thank you, Chairwoman, and good morning, ladies and gentlemen. And thank you for giving me the opportunity to present our paper. My name is Marco William Langi. I am a final year student at Physics Study Program, Faculty of Mathematics and Natural Sciences, Institut Teknologi Bandung. And I will present this paper on behalf of us, the authors, with the title A Signal Size Estimator Based on Correlation Dimension for Auditory Signal. The outline of my talk is as follows. First, I explain that in non-intrusive pre-screening of respiratory diseases, such as, among others, COVID-19, it's mandatory to measure various sizes of auditory signal, like audible sound signals, as their distinct characterizations. Next, I explain a practical estimation made possible using a Takens and Grassberger algorithm producing different estimates in each embedding dimension. The estimator consists of four processes. First is signal measures creation, second is covering counting, the third is critical exponent estimation, and the fourth is size calculation. Grassberger has published fast algorithm, culminating in a set of toolbox in design. We study the resulting estimates of controlled signals to validate the estimator as well as to come up with a calibration scheme. Here we use the estimator on three well-known signals. The first is sinusoidal, second is pink noise, and the third is Hanon chaotic signals, and studies the results to recommended calibration. In any smart systems, valid and meaningful measurements are critical, as they are used to generate knowledge upon which decision making and planning can be made, and best action can be performed. Invalid and meaningless measurement cause smart systems to fail. This is especially true in one important case, non-intrusive pre-screening. Such a system records auditory signals coming from a person's voice, especially cough. It then characterizes the signals using various algorithms, extracts parameters according to a model, and applies the decision-making scheme, including machine learning to determine pre-screening outcomes. It depends on signal characterizations that must be based on valid and meaningful measurements. We have developed a signal measurement system that depends on power law, as shown in figure as we can see right now. Our fractal estimator of signal sizes consists of mapping to a measuring space of scale R, creating a signal measures, covering counting of signal measures, fractal estimation D, and size calculation. The system takes a segment of signal as its input and produces two outputs, signal size and signal dimension. We are free to choose any measure as long as power law holds. First, we map the signal x n to a Euclidean space of dimension m. One way to do it by constructing a set of vectors of m-dimensional from input signal xn, where like j equals 1 and m equals 1 and so on until 10 is the selected embedding dimension. We then create a measure from the signal which is non-negative numbers associated with set of points from the signal. There are many ways of doing this, and we are interested in one that is scale invariant with its set size. In the case of correlation dimension, we create a ball of scale or diameter r to be applied on the signal set and define the measures as square of the probability to find a point inside the ball. The point itself is defined as a pair of two vectors, such as measure is called correlation sum. We can see correlation sum or CR is the number of point pairs that have distance less than r. Increasing r causes more pairs being counted. Thus, CR also increases, as a power law can be defined as CR equivalent to r to the power of DC. If this holds the critical exponent, this is the correlation dimension we are looking for. Having defined vectors xi, we should use bulk covering and counting other vector pairs to count CRK for several successive RK. It is, however, computationally expensive. The Tizian toolbox proposes a much faster algorithm that computes C and R instead of CR. We doubly use the so-called Taylor window, and n pairs does not have to be all possible pairs. When R is small and M is greater than 2D, this measure scales with R, for example with dm equivalent to dc, as in power law equation. For each M, we then successfully cover the signals with ball RK and count its corresponding CMRK. We can have a line equation of a log-log plot that can be obtained experimentally by first convert power law equation into a line equation. Using a linear regression, we can estimate the critical exponent dm, which is the correlation dimension at a certain m. If the object dimension is greater than space dimension, the measurement gives the space dimension. In that case, one must increase the selected space dimension and repeat the measurement. Thus, a best practice is to obtain measurement on several m and see if the results converge. The measurement will fail, like if it does not converge to a number other than the m, if the system is random, or the dimension is too high. Finally, at valid dm, we have c, which in turn gives the signal size s as c equals to log s. Alternatively, we can see the equation number 6. A segment of an auditory signal is given as the input signal xn. Auditory signal have a spectrum of frequency ranging from 20 Hz to 20 kHz. Digitizing it requires a frequency sampling of more than 40,000 samples per second. Standard sampling rates of 44,100 samples per second or 48,000 samples per second can be used. Furthermore, we limit the segment to a maximum of 10 seconds as a single cough takes a duration of 1 second or less. Data are reduced using Taylor window of 50, delay j equals 1, and n pairs equals 1000, and smoothing of the results using a Gaussian kernel. As input, we use 3 reference signals. The first is sinusoidal, the second is noise, and the third is Hanon, shown in figures 1. A sinusoidal should give a dimension of dm equals 1. A noise signal should give a very high or infinite dimension. In this measurement case, a noise signal should give dm equals m, meaning the measure does not converge. Finally, the Hanon signal should give a dimension dm equals 1.25 with the uncertainty of 0.02. Figure 2 shows dimension estimation result of sinusoidal signals. Each line represents an estimate for each embedding dimension m equals 1 until 10, from the bottom to the top. The x-axis represents the scale r in a logarithmic scale. Visual inspection of these results show that the estimator has given correct estimates for m greater than 1 and scales greater than 0.01 and smaller than 0.1. The results for noise signals are shown at the center. As expected, each line reports dm equals m. This means they do not converge. Visual inspection of these results also suggests that the valid scales are greater than 0.01 and smaller than 0.1. Finally, processing Hanon signal produces result in the right. Since we know dm equals 1.25, the results confirm this for m greater than 1. Visual inspections also suggest that the valid scale range is greater than 0.01 and smaller than 0.1. We are now ready to calculate the sizes of signals. However, we have used Tizian fast algorithm. As a result, there are CMR as many as m equals 1 until 10. This results in 10 estimates of sizes, as shown in the figure. The figure shows line from top to bottom for m equals to 1, 2, so on, respectively. We shall use line from m closest to d, m greater than equals to d, and in this hand case, m equals to 2. Furthermore, we should only consider sizes within a valid diameter range of r greater than 0.01 and smaller than 0.1. As shown in the table, local estimation results in 10 possible dimension values. Averaging the size value at m equals 2 within this range result in Hanon signal size of s equals to 0.603 for d equals to 1.25. Using local dimension d equals 1.23, we obtain s equals to 0.57. We have developed correlation dimension-based size estimator for auditory signals and verified it using 3 reference signals. The estimator takes a segment of time domain signal, typically of length 1 second, and apply the dimension estimation and size calculation. The estimator provides a set of possible dimensions at a range of measurement diameters. Visual inspection suggests that valid diameters for signals sampled at 48,000 samples per second in the interval of r greater than 0.01 and smaller than 0.1. We have confirmed the validity of measurement on 3 reference signals: sinusoidal, noise, and chaotic. The estimator produces expected results. We suggest the following steps to use this estimator for respiratory disease detection research. Collect coughs, sample of healthy group and patient group, that is, people with negative and positive COVID-19 disease respectively. Segment the samples into 1-second cough segments. Estimates dimension and size of each segment. Determine correlation between the dimension and sizes and disease parameter. As a conclusion, an auditory signal size estimator can be developed using correlation fractal dimension measurement. Possible applications include detection of respiratory diseases, such as COVID-19. Thank you.